Okay, so today we're going to cover refraction here in Physics 30. It's going to be a bit different than anything we've looked at so far in this unit. Let's get started. So covering refraction today, which is the bending of light as it passes through two or more different mediums. We're going to use something called Snell's law as a way of calculating this. It's just an equation that's on your formula sheet. We're going to look at some applications of refraction, and we're going to do a ton of examples. I don't know if we'll actually get through all of these examples here. There is a whole bunch that I've thrown in here, so we might run out of time. I'll just watch the time carefully. But if we get through them, awesome. The one thing I want to tell you again, just a reminder, is EMR Notes Part 1, which again is on Google Classroom. That's what I'm using to go through this, right? I'm following that booklet pretty much exactly. It would be really useful for you to download that. Even if you just download the one that's called the filled in solutions or something, that's where I actually put my teacher notes in there. You could use that following along as well, that's fine. The other thing I want to say though is the worksheet practice problems, they're located in this, right? Especially the blank one. So you will need to access that at some point so you can try some of those practice problems, even if you just look at them on a computer or on your phone and then do them on a piece of loose leaf paper. Anyway, let's get going. So refraction is on page 19. Refraction occurs when a light wave changes direction when passing from one medium to another due to a change in its speed. So if you had some visible light coming in from the air, as soon as the visible light touches the surface of the water, it has to change its direction to compensate for the fact that it's now in a denser medium. So the denser medium changes the speed, and light behaves in a bit of a weird way where it actually starts to bend. Now we've all seen this actually before. If you've ever seen, let's say, a fish in some water, the fish appears like it's in a direct line of sight from wherever you're looking, but in reality, it only appears that way because the light from the fish has been bent to make it look that way, right? So the fish is actually in a different location than what it seems. On the page there, there's a little diagram that says draw and label a ray diagram for partial reflection and partial refraction. There is no way that I'd be able to muster this. Of course, using this little digital pen that I'm using for this. It's way too complex of a drawing. But basically the gist of it is if you have an incident ray coming in and it's hitting somewhere right on the surface, like let's say if this is between air and water, that point that it's striking the surface is called the point of incidence. Now you're going to get a couple of rays that form from this. Sometimes it's just one ray, sometimes it's two rays with the water. It would definitely be two. You're going to get one ray that gets reflected, right? So that's why you would see a reflection in the water. But you're also going to get a ray that is refracted, right? And refracted just means it's bent. Notice how this ray didn't actually continue going straight as it would have been if this was just from air to air. It's actually bent. And because water is a denser medium, it's actually going to bend closer to your normal line than it was at when it came in, right? So we call this angle between your incident ray and the normal line the angle of incidence. And then the angle between the normal line and the reflected ray is the angle of reflection. And I used a capital R for angle of reflection, where it's very rare that we're going to use both reflection and refraction, but it's just nice to have something there to be consistent, if at all possible. And then the angle, of course, between your normal line and your refracted ray is called the angle of refraction, and I used a lowercase r to represent that one. So that's basically the whole idea here. You can jot that down in your notes, but I'm going to move on. So refractive index. The bending of light depends on the refractive index of the medium in which the light is traveling. Generally, the more dense the medium, the higher the refractive index. For those of you who have a textbook, if you're on page 667, you can actually see a list of them. I'm sure you could Google a list of refractive indices as well. You won't need this list whatsoever, but it's just nice to look at. So when light passes from air into any other medium, it is bent towards the normal line. This is, of course, because air has a lower index of refraction than pretty much anything else. Now, air has a slightly higher index of refraction than a vacuum, but in this course, it is such a small difference that we're almost never going to look at it. If a question tells you the refractive index of air versus a vacuum, and again, it goes down to like the 5th or 6th decimal place, it's like pretty extreme. Then you would use it. But otherwise, we can just assume that air and a vacuum have the same refractive index. But we'll get into that later. This means that the speed of light decreases as it enters any other medium. So the speed of light in water is actually less than what the speed of light is in air, and that's because it's a denser medium for it to travel through. So there's a general rule of refractive indexes here. The refractive index, which is n, of any medium is the ratio of the speed of light in a vacuum, which we've always denoted with the letter C, to the speed of light in the medium itself, which we'll call v. So again, your refractive index is just the plain old speed of light. That's 3.0 times 10 to the 8 meters per second, divided by the speed of light in the medium. Okay, so if it's a smaller number, if you're dividing something by a smaller number, your refractive index is going to be a number bigger than 1. So in other words, it'll have a higher index of refraction. That really implies that the lowest index of refraction you can have is 1.0, where the speed of light in a vacuum is the same as the speed of light in the medium, because you can't get any less than a vacuum. A vacuum is just empty space, right? So 1.0 is the refractive index for a vacuum. And again, like I mentioned just a minute ago, we will also assume that 1.0 is the refractive index for air as well. It's pretty darn close. Air, again, is 1.000, and then there's some other decimals way down there, but they're more or less the same thing. So Snell's law. Snell's law is something we can use to actually compare this mathematically. The mathematical relationship between the angle of incidence and the angle of refraction was identified by Willebrord Snell. The general form of Snell's law applies in all cases, regardless of the media. So it doesn't matter if it's going from air to water or vacuum to glass or whatever, Snell's law is still going to apply. So what Snell's law says is sine of your angle of incidence divided by sine of your angle of refraction is equal to some constant. This part of Snell's law is not going to be super useful. I'll make it more useful for you in a second, but basically the constant indicates the amount of change between your angle of incidence and your angle of refraction. It also corresponds to the index of refraction, that was the n, of the two mediums. There's a relationship here. Let me show you a little bit more in detail. So if the first medium is air or vacuum, because again, both of them have n equals 1, Snell's law can be reduced to sine of your angle of incidence over sine of your angle of refraction is equal to n of the new medium. So let's say you were going from air to water. This would be what you would use to find the refractive index of water. So again, the refractive index of vacuum is defined as being 1.00. Here's the decimal I was looking for. The refractive index of air is 1.00029. So it wasn't quite to 6 decimal places as I had thought, but still pretty darn close. That's pretty darn close to 1. So generally you can assume it to be 1.00 under normal applications, but if it ever tells you otherwise, if it ever gives that to you, then you can use that. So Snell's law expanded. This is where it's really going to be useful. This is the real form of Snell's law that we're mostly going to be caring about here. Snell's law can also be applied to wavelength and speed. Remember, wavelength and speed are two properties of electromagnetic radiation that are related back to the speed of light itself. So the expanded form of Snell's law, this is on your formula sheet, don't you worry. Again, it's sine of theta 1, which is usually your angle of incidence, divided by sine of theta 2, which is usually your angle of refraction, equals n2 over n1, which equals v1 over v2, which equals theta 1 over theta 2. This is not a typo here. The fact that it's n2 over n1, whereas all the other ones have 1 on the top, that is how it's supposed to be. So imagine this. Imagine that your situation for 1 was something coming from air, and your situation for 2 is it going to water. This could be reread as saying the angle of incidence when it's in the air, and this would be the angle of refraction when it's in the water. This n2 would be your index of refraction, because n is your index of refraction for water, and n1 is your index of refraction for air. v1 would be the velocity of your light wave in air, which is just the normal speed of light. v2 would be the velocity of your light wave in water. Theta 1 would be the wavelength of your wave in air, and theta 2 would be your wavelength of the light in water, right? So any pair of these ratios can be used in an equation. So you could say that this piece equals this piece, right? Or that this piece equals this piece, or whatever any other relation you can come up with. This is a very versatile giant formula here, right? Again, this is on your formula sheet. Remember from the last slide, if the first medium is air or a vacuum, n1 can just be ignored because it's basically 1. That's why we said on the last slide that sine of angle of incidence over sine of angle of refraction is equal to your new medium's index, because you're dividing by 1 here. n1 would just be 1 if it was air or a vacuum. Moving on. A couple other terms we've got to know here. One is total internal reflection. This is where reflection of all incident light is back into a medium of higher refractive index. due to the inability to refract light beyond the maximum angle of 90 degrees. Basically, this happens if something is trying to leave a dense medium to something that's not so dense, and the light just literally gets reflected inside of it. In other words, it's not even able to refract to the other surface. And critical angle is the size of the incident angle, which would result in that angle of refraction of being exactly 90 degrees. So in other words, it's that incident angle that would first start giving you total internal reflection. Here's an image kind of showing it. Let's say you had a light source in the denser medium, which is water, and you were beaming the light out towards the air. Well, this one, because it's going straight on, is just continue going straight on, right? There's no angle of incidence from the normal line. It's 0 degrees, so it's just going to continue onwards. But for these light beams, they're going to have different angles of incidence. So this one, for instance, has an angle of incidence of 20 degrees. And then when you do the calculations, you see in air, the angle of refraction, when it's up in air, that would be your N2 in this case, would be 27 degrees. They did the math on these other ones, they got this, but eventually they noticed when you had an angle of incidence of 50 degrees, it actually stayed within it, right? It didn't actually leave. There was no like full-on refraction going on. Well, there was a refraction. It just went all the way around and then came back down to here. Eventually, somewhere in between, you would have some sort of a light beam where it hits, and then this angle of refraction, because notice it's going up, 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 eventually that angle of refraction would be 90 degrees from that normal line. That right there would be called your critical angle. So your critical angle would equal that angle of incidence that produced that right triangle angle of refraction. Oop, lowercase r, angle of refraction right there. So that right angle of refraction is produced by the critical angle theta I. Again, that's total internal reflection. Total internal reflection is where it didn't escape, it stayed within. Now, some applications of this. One application, if you wanted to fill this in the notes, if you actually have that out, is optical fibers, which of course are used to transmit modern internet, phone, and TV data. Optical fibers are very efficient, they work very well, and basically it just works by ensuring the beam of light stays within the cable as it passes through the entire optical fiber. It's a bit more complicated than that, but that's a simple way of looking at it. All right, prisms. When white light shines through a prism, the light is broken up into a spectrum of color. You get like a whole rainbow that gets formed from it, right? Now the reason for this is because white light is actually made up of all the colors from red to violet. Each color has a different wavelength. Here we go, a different wavelength. And light of differing wavelengths will refract through the prism at different angles. They'll have different angles of refraction. Violet has a shorter wavelength and is refracted, therefore, at a larger angle. This occurs because violet light slows down more than red light when entering the prism. Now, these forms of light, they're all going to have the same speed as long as they're in the same medium. But again, different colors of light have different wavelength, and that still plays in Snell's law, because remember, wavelength is denoted by the symbol lambda. Now, because violet light refracts more than red in the same prism, violet light has a higher index of refraction than red light does. Moving on. Here's a good picture showing that, of course, when you have white light that enters a prism, the reason it separates into all these different colors of the rainbow is because the different wavelengths that make up the different colors of light that are within this are all going to refract at different angles, right? So in other words, some will refract at a bigger angle than others. So we have a few examples I'd want to go through here. We actually are doing pretty darn good for time, so I'll see what I can get through. So a ray of light strikes the surface of a block of an unknown clear material. The incident angle is 72 degrees and the angle of refraction is 39.3. What is the index of refraction for the unknown material? Okay, so since it's striking the surface of a block, we can actually assume that it's entering from either air or a vacuum. Hold on, entering from air or a vacuum. We can make that assumption. That is a valid assumption to be making here. So therefore, N1 is just 1.00. Now, since we're looking for the index of refraction, that's theta r, then it would probably be wise to use the formula that says sine theta 1 over sine theta 2 equals N2 over N1. Now from here, we know our theta 1. Theta 1 is your incident angle. So we have sine of 72.0 degrees over sine of our angle of refraction, which is unknown, so theta 2 equals N2, which Oh, sorry, my mistake. What am I talking about? Angle of refraction is known. It's 39.3. There I go, goofing up already. Again, angle of refraction, 39.3. What we don't know is our index of refraction for the unknown material. My mistake, sorry about that. N2 over 1.00. Bottom line is to find N2, because this is just 1, it's really not doing anything at all. We just have to divide these two. And again, make sure if you're plugging this in your calculator, make sure you're in degree mode, especially for those of you in Math 30 right now where we're jumping back and forth. Make sure you're in degree mode. Either way, you're going to get N2 equals 1.50, and that is to 3 sig digs. So we are good with our answer on that one. And in case you're wondering, I don't think I mentioned it earlier, an index of refraction doesn't have any units. It's just a number. It's an index, right? It's like a coefficient kind of thing. So we don't need any units on that one. Next one, ultraviolet radiation travels from air to plexiglass, and it tells us N is 1.52, clearly talking about plexiglass, and then into water, N is 1.33. Ooh, okay. The UV rays are incident on the plexiglass, so that's the first surface, at an angle of 59.0 degrees. Determine the angle of refraction as the UV rays enter the water. Okay, I think the first thing we should do is find our angle of refraction after it enters the plexiglass. Because again, it's going from air to plexiglass to water. Air, plexiglass, and then water, H2O. There you go. So it's going through all this, okay? So if we want to find our angle of refraction in plexiglass, the angle of refraction in plexiglass is going to become the angle of incidence once it enters the N2. So we can say sine theta 1 over sine theta 2, where 1 is air and 2 is plexiglass, equals N2 over N1. Or in other words, sine of our incident angle, which it told us was here, 59, over sine of our angle of refraction, theta 2, which this time it didn't give it to us, so that is what I'm looking for here, equals N2, which is 1.52, over N1, which is 1.00. We just need to rearrange this formula. Of course, you can divide these and then times by sine theta 2 and then divide that over. And you're going to find, I'll just save us the trouble. Oh, you divide it over and then you have to take the inverse sine, of course. But I'll save us the trouble of all this. I'll assume you know how to do this because we've done questions like that before. Theta 2 is 34.3 degrees. Now, what you need to realize is this theta 2 is going to become your first incident angle when you enter the water. So here's what we can do now. We can now say that this becomes our new theta 1, right? And what we're looking for is our angle of refraction, so our new theta 2 in a secondary equation here, right? Let's have a look here. So we are saying that this is our first theta now. We can say that's therefore sine 34.3. We're looking for theta 2, so sine theta 2. And let's see what equation we'd have to use. We'll try to use n again. Well, n1 would be your plexiglass now, and n2 would be your water. So we have to say n2 over n1, so 1.33 this time, over our n1. And remember, since we're going now from plexiglass to water, our n1 is 1.52. Again, divide these, multiply this over, divide that over, and then take the inverse sine of it. Again, assuming you know how to do that. If you don't, please send me an email. That's going to be equal to 40.1 degrees, and that would be your answer on that one. That's the angle of refraction as the UV rays enter the water. We'll do a couple more here. I know we're kind of getting short of time. Determine the speed of light in water, and it tells us n is 1.33. Well, on your formula sheet, part of Snell's law says V1 over V2 equals N2 over N1. Remember, any two parts of that equation can be used to solve these kinds of problems. So since we're determining the speed of light in water, how about let's just say, because it doesn't tell us which way we're going, let's just say N1 is air and N2 is water. Well, if N1 is air, then that means V1 is the velocity of light, or the speed of light, I should say, in air. And the speed of light in air is known. It's 3.00 times 10 to the 8. That is on your formula sheet, just by the way. Divided by V2, which is the speed of light in water, equals N2, so index of refraction in water, which is 1.33, divided by N1, which is just 1.00, because we can assume it's for air or for a vacuum. Again, it does not matter here because they didn't tell us. We just need to find V2, so you divide these times by V2 and divide it over. Long story short, V2, the speed of light in water, should be 2.26 times 10 to the 8 meters per second. So it did slow it down a fair bit. I compare that back to this number here. It did slow it down by about a quarter or so, but still, it's good to know. Moving on to the next one. A ray of yellow light with a wavelength of 570 nanometers, that's what NM means, travels from air into diamond, and diamond is N equals 2.42, at an angle of 30 degrees. Determine the wavelength of the light as it travels in the diamond. So just a little bit of a heads up, because we don't see this unit too often, but believe me, you're going to see it more often as time goes on. NM is a nanometer. That just means times 10 to the -9. And again, that is on your formula sheet. They do have a metric conversion chart on your formula sheet. Nano means times 10 to the -9. So really, this is 570 times 10 to the -9 meters. That's what that really means. So we're looking for the wavelength of the light as it travels in the diamond. So in other words, we can say wavelength, which is theta. We can use a part of Snell's law that would say theta1 over theta2. Sorry, why did I say theta? Lambda 1 over lambda 2. My mistake, guys, sorry. It's really a rough day. Equals N2 over N1. Well, lambda 1 would be the wavelength in air. So the wavelength of the yellow light in air, which would be this. We're looking for the wavelength when it's in the diamond. We know N2 being the refractive index in the diamond, and N1 we can assume is 1 because, again, it's from the air. So let's just throw those numbers in there. Why did I just say them out? I could have written them down the whole time. 570 times 10 to the -9 over lambda 2 equals 2.42 over 1. I'm not even going to write 1.00, it's just a waste. Multiply this over, divide by 2.42, and you're going to get lambda 2 equals 2.36 times 10 to the -7 meters. Notice how quick these go? Like, they're not a ton of work. They're just kind of more or less saying, all right, what do I have in the question? And if it really helps you, another strategy you can use is like actually label them. It's got this wavelength traveling from air into diamond. So you say, okay, that's the lambda 1. That would be N2. Oh, it even gave us an angle. Well, we didn't have to use the angle here. See, I just naturally just threw it all together based on what I was given and what I wanted. I wanted that wavelength, so I knew I had to use this relationship. And then as soon as I saw this N2, I was like, well, we got to use this one because we know N1 is 1. But again, it can be a bit of a puzzle. That's about the hardest part with all this. Just because we still have time, I'll go over, like, there's 2 more questions. We'll go over as much as we can. This one actually will be a really good one to go over. Actually, I remember this one. So light from a green laser, we have the wavelength is 544 nanometers. Traveling through ice, which is N equals 1.52, strikes the edge of the ice-air interface with an angle of 60 degrees. What is the angle of refraction? So it's traveling through ice, and then it's going to air. So we can actually say ice here is our N1, and we'll say that our N2 this time is the air, which is 1.00. Now, it's striking the edge of the interface with this angle, so this is actually our theta1, and we're looking for angular refraction, so we're looking for theta2. I think they've kind of spelled it out for us exactly what formula we've got to use. We've got to use the one that says sine theta1 over sine theta2 equals N2 over N1. And remember, that one is always backwards, okay? Anyway, sine theta1 is sine 60 over sine theta2. That's going to equal N2 is 1.00 this time around, and N1 is 1.52. Because we're going from ice to air, it's important you have that order correct. You can't just label them whatever you want. Anyway, we would have to multiply this over, and this one, believe me, I'm going to do a little bit different. I'm actually going to show you some of the inner steps here. If you divide this and then times this over and then take whatever this division number is and go sine 60 divided by it, you're actually going to find that sine theta 2 equals 1.31636. Now, for those of you in Math 30 right now, hopefully you're looking at this and going, wait a minute, that's not possible. Sine of an angle is never outside of -1 to +1. But this is bigger than +1. If you tried to take the inverse sine of this to find your theta 2 here, it's just going to give you an error. Well, this is because there is no solution. But in terms of physics, what does that mean? Well, what that means is it tells us that our theta r, our angle of refraction, must be greater than 90 degrees. I don't know why I drew that. 90 degrees, there we go. So in other words, this is total internal reflection. You've passed your critical angle. You're beyond that. So in other words, there won't be a true angle of refraction. It's just going to stay within the ice when it hits it at that angle. It's too steep of an angle. That light isn't going anywhere. It's not leaving the ice. All right, last one. We do have time for this. I will go through it. I'm actually quite impressed that we actually were able to get through these all. If the index of refraction for quartz glass is 1.47, determine the critical angle for the quartz glass air interface. Well, remember, in order for a critical angle to occur, you have to be going from dense to less dense. That's how it has to happen. So we can therefore say that our dense piece, which is the quartz glass, that's going to be our N1, and we'll say that N2 is our refractive index for air, which is 1.00. Now we're looking for the critical angle. Critical angle is defined as being where your angle of refraction equals 90 degrees. So if we're looking for the critical angle is the angle of incidence that gives us that angle of refraction being 90 degrees. So I think we've kind of laid this out. We know we need our theta 1, that's our angle of incidence. We know that our theta 2 is 90, and then we know N2 is air, and N1 is 1.47. So now that we have this set up, it's just a matter of multiplying by sine 90 on both sides, and then taking the inverse sine of whatever that answer ended up being. This is going to give us theta 1 equals 42.9 degrees. In other words, that is your critical angle, or to put it yet another way, that is the maximum angle that you could shine the light at in order for it to actually refract out into the air. If you did it at any angle more than that, you would have total internal reflection and the light would not be leaving the quartz. So we're done. So what I want you to do is work on the refraction worksheet. That's page 24 to 28 in the EMR notes booklet. Again, that is found on Google Classroom. And as always, if you have any questions, please contact me by email or over Remind or even on Classroom.